Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine sending a probe to the absolute coldest, darkest edges of our solar system. You're expecting to find a completely frozen static block of ice. Right.
Right. I mean, that's what the math and the textbooks basically told us to expect for decades.
Exactly. But what if decades later you realize you might have actually been looking at an ocean of boiling magma the entire time?
It's wild to even think about. It completely flips our entire understanding of planetary physics on its head.
It really does. And, for almost 40 years, our science textbooks, the classroom posters we all grew up looking at, our whole conceptual framework for the outer solar system might have just been lying to us.
Yeah, unintentionally lying, of course, but lying nonetheless. We've been so incredibly confident in our labeling.
We really have. I mean, think about those classic planetary neighborhoods we learned about as kids. You've got the rocky inner planets near the sun, Earth, Mars, Venus.
Sure.
Then you have the massive gas giants, Jupiter and Saturn, just dominating the middle.
Vacuum cleaners of the solar system, yeah.
Right. And then, way out in the freezing dark, practically hovering right on the edge of interstellar space, you have Uranus and Neptune. And the label pointing to them has always been so definitive. They are the ice giants.
And it's a label that paints a very specific, very rigid picture for people. When you hear ice giant, your mind is essentially forced to imagine a dormant world, like a planetary deep freeze.
Yeah, a giant snowball.
Exactly. And for a really long time, the scientific community leaned heavily into that categorization because it fit the very limited observational data we had at the time. And quite frankly, it made the mathematics of planetary formation in the outer solar system somewhat manageable to calculate.
But as we know, science is entirely dependent on anomalous data. Right?
Yeah.
Like when observations refuse to fit the established model, eventually that model just has to break.
It has to break. And in this case, the model isn't just breaking, it's having a complete meltdown, literally.
Literally. So today, we are going to explore this fundamental rethinking of our own solar system. It's a massive paradigm shift proposed by a team of researchers at UCLA, led by Edward D. Young and his colleagues.
Right, and they are suggesting something that sounds almost like science fiction. They're saying that beneath the atmospheric clouds of Uranus and Neptune, we aren't going to find hundreds of thousands of miles of slushy frozen ice at all.
No ice.
No. Instead, we are likely looking at massive, violently churning oceans of liquid magma.
Okay, wait. Magma. Like volcanoes on Earth kind of magma.
Exactly like that, but on a scale that is almost impossible to comprehend. It completely changes the paradigm. And what is so compelling about this UCLA study is that it isn't simply an exercise in being contrarian just for the sake of it,
They aren't just trying to be edgy planetary scientists.
No, not at all. This magma ocean model is attempting to solve two of the most glaring, incredibly frustrating puzzles in modern astronomy, specifically the bizarre magnetic fields and the completely inexplicable heat distribution of these two planets.
Puzzles that have basically baffled people since the 1980s.
Exactly. For decades, astronomers have essentially been trying to force a square peg into a round hole. They've been trying to make this static ice interior somehow explain highly dynamic, chaotic planetary behavior.
Because, if a solid block of ice traps heat, what state of matter actually allows that deep primordial heat to escape? And how on Earth do you get complex, twisting magnetic fields from a frozen core?
You don't. You simply don't. And those are the exact physical contradictions that drove this new research.
But before we dive headfirst into the magma, I think we need to understand how we got so locked into this ice giant mindset in the first place. Because it's not like planetary scientists just looked at how far they were from the sun and lazily assumed everything out there was a giant ice cube.
Right. There was actual methodology behind it. There was a logical progression based on the math.
So walk us through that. How did the textbooks get written this way?
Well, the math essentially forced early astronomers into a corner where ice seemed like the only plausible conclusion. So If you look at Jupiter and Saturn, their composition is primarily hydrogen and helium.
Just massive balls of gas.
Exactly, because they formed close enough to the sun and they gathered enough mass quickly enough to just sweep up massive amounts of these really light gases from the primordial solar nebula. They are the true gas giants.
But Uranus and Neptune are a different story.
Very different. They are much smaller than Jupiter, but crucially, they're significantly denser.
Okay, so they couldn't just be made of pure hydrogen and helium. The sheer density implies there has to be much heavier stuff packed in there somewhere.
Precisely. The way you figure this out is, well, you calculate the planet's mass based on its gravitational pull on its moons, and then you calculate its volume based on its visual size through a telescope.
Standard geometry.
Right. And when you divide mass by volume, you get this very specific intermediate density. It's much heavier than a pure gas giant, but it's still way lighter than a dense, rocky, terrestrial planet like Earth or Mars.
So they were looking for a Goldilocks material, something not too light, not too heavy.
Exactly. So they asked themselves what fits that intermediate density profile. And in the context of the cosmic abundances of elements, what was actually available out there when the solar system formed, the most likely candidates were volatile compounds.
Meaning things like water, ammonia, and methane.
Yes. Water, ammonia, and methane. And because the ambient temperature in that region of the solar system is, hundreds of degrees below zero, the assumption was that these compounds had to exist in a frozen or maybe heavily slushy state.
Because obviously it's freezing out there.
Right, that was the foundational logic. So the traditional model posited this relatively thin outer atmosphere of hydrogen and helium acting like a blanket, hiding a vast, incredibly thick mantle made entirely of these highly pressurized ices, and all of that was wrapped around a smaller, rocky core.
Okay, that makes sense on paper. But the crucial context here, and this is the thing that I think is almost impossible for the average person to really wrap their head around, is the sheer lack of actual empirical data we have to support that old model.
Oh, the data drought is staggering.
I mean, humanity has only visited these planets one single time. Once. NASA's Voyager 2 spacecraft flew by Uranus in 1986, and then it reached Neptune in 1989. That's it.
And that's all we have. Every textbook diagram, every CGI documentary rendering of their interiors you've ever seen essentially stems from those two incredibly brief encounters.
It's wild to think about. Voyager 2 is obviously one of the greatest engineering achievements in human history, but we have to remember the context of its technology. The spacecraft was built in the 1970s.
It was recording data on actual magnetic tape.
Yes. Magnetic tape. And it wasn't even orbiting these planets. It was performing flybys. It was screaming past them at tens of thousands of miles per hour.
It's an incredibly constrained snapshot.
It's like trying to understand the entire complex ecosystem of the deep ocean by just quickly driving a speedboat over the surface of the water once in 1986.
Yeah.
Like you take a couple of Polaroids as you zoom past, and then you spend the next 40 years trying to build a comprehensive, highly detailed model of the Marianas Trench based solely on those blurry photos.
That is an excellent way to frame it. Obviously, the models you build from that are going to have massive, massive blind spots.
So what did those brief Polaroids actually show us? Because clearly they saw something that didn't quite make sense.
Well, Voyager 2 measured a few key things. It measured the atmospheric compositions at the very top layer. It recorded the thermal emissions, the heat radiating out into space. And crucially, it measured the planetary magnetic fields.
And here's where it gets really interesting. The magnetic fields.
Yes, it was that last measurement, the magnetic field data, that immediately threw the scientific community into a state of total confusion, because the data simply did not align with the ice giant model they had constructed.
Let's get into the mechanics of that, because this seems to be the first major thread that eventually unraveled the whole icy paradigm.
Mm-hmm.
Now, I'm familiar with Earth's magnetic field. It's what makes a compass work, right?
Right.
And magnetic north is relatively close to the actual geographic North Pole. It's somewhat aligned with how the planet rotates. So what did Voyager 2 actually find when it looked at Uranus and Neptune?
It found sheer chaos, absolute chaos.
How so?
Well, to understand why it was so anomalous, we have to look at how planetary magnetic fields are generated in the first place. They aren't just giant, permanent magnets sitting dead in the center of a planet. They are actively generated by a complex process called a planetary dynamo.
A dynamo. Okay.
Yeah, and for a dynamo to work, you need a massive volume of electrically conductive fluid deep inside the planet, and that fluid has to be physically churning and convecting.
Like boiling water.
Exactly. On Earth, that churning fluid is our liquid iron outer core. The planet rotates, the intense heat makes the liquid iron convect upwards, and then the Coriolis effect from the rotation twists that moving conductive fluid into these complex spiraling columns. And that movement generates a massive, relatively stable magnetic field that roughly aligns with our axis of rotation.
Okay, so the rotation of the planet basically organizes the chaotic churning of the liquid metal into a neat, structured, planetary-scale magnetic field.
Under normal circumstances, yes, that's the ideal model. But Voyager 2 revealed that the magnetic fields of Uranus and Neptune are heavily tilted. I mean, severely tilted. We're talking 59 degrees off the axis of rotation for Uranus.
Wow, 59 degrees, that's almost sideways.
It's completely skewed. And for Neptune, it's 47 degrees. But wait, it gets weirder. Furthermore, the magnetic fields aren't even centered.
What do you mean not centered?
They don't originate from the geometric core of the planets. They are completely off-kilter, practically emerging from the sides of the planets rather than the center.
That makes no sense. So if we picture the planetary dynamo as a spinning top, Earth's dynamo is like a perfectly balanced top spinning upright. But Uranus and Neptune have dynamos that act like a spinning top with the heavyweight glued to one side. It's wobbling, it's chaotic, and it's completely unstable.
That mechanical instability is the key issue here. Because if Uranus and Neptune were primarily composed of a thick mantle of water, ammonia, and methane ice, you run into a massive physical contradiction.
Because ice isn't a churning fluid?
Exactly. Even if we assume the extreme pressures in the interior create exotic forms of ice-like, there's a theoretical state called superionic water, which is somewhat conductive. It still behaves far too rigidly. Ice, by definition, resists the rapid, turbulent convection required to produce a highly active dynamo.
It's too stiff.
Way too stiff. And even if it could somehow convect slightly, a thick, uniform ice mantle should theoretically produce a much more centralized, neatly aligned magnetic field. It absolutely shouldn't produce the chaotic, off-center mess that Voyager 2 observed.
So the physics just break.
Entirely. The physical properties of ice simply do not support the magnetic reality of these worlds. It was a glaring contradiction from day one.
And the magnetic field wasn't the only thing that refused to make sense, right?
Yeah.
There's also the glaring problem of how these planets handle heat.
Oh, yes. The thermal anomaly is arguably even more perplexing than the magnetic one. Because planets are not just cold, dead rocks floating in space. They possess immense internal heat.
Where does that heat come from if they're so far from the sun?
Some of it is primordial heat. It's energy left over from the violent accretion process of their actual formation. You know, when countless planetesimals and space rocks smashed together over billions of years, converting all that kinetic energy into thermal energy.
So just the violence of birth creates heat that lasts billions of years.
Exactly. And some of it also comes from the slow gravitational contraction of the planet over time. But regardless of the source, this intense internal heat eventually has to make its way from the deep core up to the surface, where it can finally radiate out into the vacuum of space.
And the way that heat naturally travels through a fluid is primarily through convection, right? Just like a pot of soup on a stove. The hot material deep down becomes less dense, it rises toward the cooler surface, releases its heat, becomes denser again, and sinks back down. A continuous rolling cycle.
That's it. Convection is the absolute primary engine of planetary heat transport. But here is where the old ice giant model completely fails again. A massive, thick layer of pressurized ice, even slushy, exotic ice acts as a phenomenal thermal insulator.
It's basically a giant planetary thermos.
Yes, it severely dampens any convection. If Uranus and Neptune were truly ice giants, that thick icy mantle would essentially trap the primordial heat deep, deep in the core. It wouldn't be able to escape efficiently.
But that's not what we actually see when we look at them, is it?
Not at all. The surface temperatures and the specific infrared radiation profiles that Voyager 2 measured and, that our modern telescopes continue to observe today, they show a highly dynamic heat flow. It strongly implies active, vigorous convection from the inside out.
I remember reading a crazy stat about Neptune. Doesn't it radiate way more heat than it even gets from the sun?
It does. Neptune radiates more than twice as much energy into space as it receives from solar radiation. That massive amount of internal heat is escaping somehow. It is not being insulated by a static block of ice.
It feels like this massive cosmic historical irony. We literally gave them this incredibly specific moniker, ice giants, that actively, fundamentally contradicts the actual physics we are observing.
It really is ironic.
I mean, we are watching them generate complex, highly energetic magnetic field, and we are measuring massive amounts of heat actively flowing out of their deep interiors. Both of those things require fluid, dynamic, chaotic movement. Yet we slapped a label on them that implies a frozen static insulatory state. The name itself basically became a psychological barrier to actually understanding the physics.
Which is exactly why Edward D. Young and his team at UCLA decided they had to discard the label entirely. They approached the problem from a completely blank slate. They didn't ask, how can we somehow mathematically force ice to fit this weird data?
Right, which is what people had been doing for decades.
Exactly. Instead, they asked, what specific internal structure, regardless of our preconceived notions, naturally produces the magnetic and thermal signatures we actually see?
They just followed the evidence.
They did. They utilized highly advanced computer simulations tools that were, completely unavailable to the scientists during the Voyager era in the 80s. They used these massive supercomputers to model the deep interiors based purely on the raw laws of thermodynamics, fluid dynamics, and high-pressure chemistry.
Okay, let's unpack this.
Yeah.
Because this leads us right to the core of this whole paradigm shift. The UCLA models completely toss out the traditional massive block of ice, and they replace it with a highly complex three-layer internal architecture.
Right. The three-layer model is incredibly elegant because it actually resolves all of those decades-old contradictions. So if we were moving from the outside of the planet inward, the first layer is the atmosphere.
Okay, so that part hasn't really changed.
No, this is the one part of the old model that remains largely intact. It's a massive gaseous envelope composed primarily of hydrogen and helium, along with trace amounts of methane, which is actually what gives both planets their beautiful signature blue hues.
Right, the blue we see in all the photos.
Exactly. And dynamically, this top layer is essentially responsible for the final stage of heat transport. It carries the internal thermal energy up to the upper atmosphere where it finally radiates out into the vacuum of space.
Okay, so the gas blanket makes total sense. That's the part we can actually see through our telescopes.
Yeah.
But what happens beneath that hydrogen and helium atmosphere? Because in the old model, this is exactly where you'd hit that endless insulating wall of ice.
Right. But in the new UCLA model, beneath the atmosphere, you enter the second layer, which they call the boundary layer. And it is so crucial to understand here that planetary interiors are not always sharply defined, like the neat layers of an onion.
It's not just gas, and then a sudden hard floor.
No, not at all. At these extreme depths, the pressure and temperature are so intense that they alter the very nature of chemistry. So the boundary layer is this massive, highly pressurized transition zone. It is a complex, multi-component chemical soup containing hydrogen, helium, magnesium, silicon monoxide, and oxygen.
Okay, I have to pause on the chemistry there. Magnesium and silicon monoxide.
Yeah.
Why are those specific elements so crucial? That sounds less like the inside of a frozen planet and way more like the inside of an industrial blast furnace.
Well, it is very much like a blast furnace. The presence of magnesium and silicon is the absolute key indicator of what lies beneath them, because in planetary science, we deal extensively with this concept called miscibility.
Miscibility, like how well things mix.
Exactly. It's essentially the ability of two different substances to mix together. Think of oil and water. They are immiscible under normal conditions on Earth, right?
They separate, right? The oil just floats on top.
But when you introduce unimaginable extreme heat and millions of times the atmospheric pressure of Earth, substances that normally wouldn't ever mix begin to fundamentally dissolve into one another. The boundary layer is exactly that, a region where the lighter gases from the upper atmosphere are violently interacting with and dissolving into the heavier, rocky, molten materials rising up from below.
Oh, wow. And those heavier molten materials are coming directly from the third layer, the main event.
Yes, the basal magma ocean.
It just sounds crazy to say out loud.
I know, but according to these new simulations, the vast majority of the interior volume of Uranus and Neptune is not ice at all, but a deeply buried, violently churning ocean of liquid silicate magma, liquid iron, and dissolved hydrogen.
I think this is the exact point where the average person's intuition about space just completely breaks down. We're talking about planets situated nearly 3 billion miles away from the sun. The ambient temperature of the vacuum around them is roughly 350 degrees Fahrenheit below zero.
It's unimaginably cold. So how on Earth does a planet sitting in the literal freezing depths of the outer solar system maintain a churning ocean of liquid rock and iron?
It is a phenomenal question, and it requires us to completely separate the concept of surface temperature from internal thermodynamics. The internal heat of a planetary interior has almost nothing to do with the sun. It is a completely self-contained energetic system.
So it's surviving purely on that primordial heat you mentioned earlier, the heat left over from its violent birth billions of years ago.
Primordial heat is the absolute foundation, yes. When a planet forms, the kinetic energy of millions of asteroid-sized bodies slamming together over millennia is converted into intense thermal energy.
Oh.
But the reason that heat is maintained as a boiling liquid magma ocean billions of years later comes down to the sheer crushing force of gravity.
The pressure.
Exactly. The immense mass of the hydrogen and helium atmosphere, combined with the dense boundary layer beneath it, is pressing down on the core with unimaginable weight. We are talking about pressures millions of times greater than what we feel standing on the surface of Earth. And as any basic high school physics class teaches us, when you exponentially increase pressure, you exponentially increase temperature.
Exactly. The extreme gravitational pressure essentially locks the primordial heat inside, keeping everything melted. But crucially, unlike a solid static block of ice, a liquid magma ocean is highly conductive and highly fluid. It can convect.
Which solves our heat problem.
Yes. The intense heat at the very core of the planet warms the liquid silicates and the iron, making them buoyant. The superheated magma rises toward the boundary layer, releases its thermal energy, cools slightly, becomes denser, and sinks back down. This continuous, violent churning creates a massive planetary-scale convection engine.
So magma is physically carrying the heat from the deep core up to the boundary layer, and then the boundary layer transfers it to the gas atmosphere, which finally radiates it into space. The whole insulation problem of the ice model is just gone.
The thermal equation finally balances perfectly, but more importantly, the magma ocean model beautifully solves the magnetic anomaly as well.
Right, the off-center wobbling spinning top.
Exactly. Remember those chaotic, heavily tilted magnetic fields observed by Voyager 2? Well, a deep, churning ocean of highly electrically conductive silicate magma and liquid iron, violently convecting under extreme pressure. That is the exact physical mechanism required to generate a chaotic dynamo.
It fits perfectly.
It does. The complex fluid dynamics of liquid rock moving at those extreme depths naturally produce the skewed, highly asymmetrical magnetic signatures that the old ice model completely failed to explain.
It's so elegant. So that boundary layer basically acts like a highly pressurized chemical filter. It allows the heat to transfer upward, but it interacts with the magma just enough to keep the massive liquid ocean contained below, all while feeding those chaotic magnetic loops.
That's a great summary, yeah. The data from Voyager 2 wasn't wrong. Our fundamental assumption about what state of matter existed at those pressures was just wrong.
And realizing that error, it feels like it opens up an entirely new avenue of astrophysics. Because the implications of this UCLA study, they don't just stop at the edge of our solar system.
Oh, not at all. If we connect this to the bigger picture, redefining Uranus and Neptune might actually be the single most important breakthrough we've had for understanding the rest of the galaxy.
That is a massive statement. I mean, how does a magma ocean on Neptune help us understand the Milky Way?
It all comes down to planetary demographics. Over the last 2 decades, thanks to incredibly sensitive instruments like the Kepler Space Telescope, we have discovered thousands of exoplanets orbiting other stars.
Right, the exoplanet boom.
Exactly. And when astronomers compiled a census of these distant worlds, they used detection methods like planetary transits.
That's when they measure the slight dimming of starlight as a planet passes in front of its host star.
Right. The transit method allows us to calculate their physical size and their orbital periods. And what we have found through all these surveys is that the galaxy is absolutely dominated by one specific class of planet, a class that we call sub-Neptunes.
I've heard the term sub-Neptune thrown around in various exoplanet surveys, but what exactly constitutes one? Are we just talking about physical size, or is it an assumption about their composition?
It's primarily a size classification, but one that strongly hints at their internal composition. A sub-Neptune is defined as an exoplanet with a radius roughly between 1.5 and 4 times the radius of Earth.
Okay, so bigger than us, smaller than the gas giants.
Precisely. They sit right in the middle of this major planetary demographic gap. They are significantly larger and more massive than rocky terrestrial worlds like Earth or Venus, but they're definitively smaller than massive gas giants like Jupiter or Saturn.
Which brings up a glaring, almost absurd cosmic irony to me. If sub-Neptunes are literally the most common type of planet in the entire galaxy, Why don't we have one?
It's so frustrating.
Right. We have small rocky planets, we have massive gas giants, and we have Uranus and Neptune, which sit just slightly above that sub-Neptune size cutoff. But we don't have a true textbook sub-Neptune in our own backyard to easily study.
It is arguably one of the most frustrating blind spots in all of exoplanetary science. Because we don't have a local analog, understanding how sub-Neptunes form, what their internal structures actually look like, and how their atmospheres evolve has been heavily reliant on theoretical guesswork.
We're just throwing darts in the dark.
Pretty much. Are they scaled up rocky super-Earths with incredibly thick atmospheres, or are they scaled down gas giants with massive, crushing hydrogen envelopes? Until now, we just haven't had a reliable local baseline to compare them to.
But the UCLA study changes that baseline completely, because if Uranus and Neptune aren't unique, weird, anomalous balls of ice, but rather complex magma-filled worlds, how does that apply to the sub-Neptunes that are light years away?
Well, the researchers fundamentally argue that the physics of planetary formation are universal. A planet's basic internal chemistry and its physical state shouldn't be drastically different simply because it formed around a different star. The physics of pressure and heat are the same everywhere. So, the brilliant insight of the Young study is that the atmospheric signatures we are just now beginning to detect on distant sub-Neptunes, using super advanced instruments like the James Webb Space Telescope, those signatures closely resemble the predicted atmospheric chemistry of a planet with a deep, boiling magma ocean.
Oh, wow. Wait, so this implies that the boundary layer we discussed earlier, that violent transition zone where magnesium and silicon monoxide are interacting with the hydrogen atmosphere, that isn't just a quirk of Uranus.
No.
It's a universal mechanism.
Exactly. The magma ocean and its complex boundary layer impose very specific, very rigid chemical constraints on the atmosphere above it. As the magma violently churns and interacts with the hydrogen envelope, it physically dictates what chemical compounds are absorbed into the magma, what is outgassed into the air, and ultimately what the upper atmosphere looks like to our telescopes here on Earth.
So the UCLA studies are basically suggesting that Uranus and Neptune are the perfect, scaled-up analogs for the most common planets in the universe.
They are our cosmic Rosetta Stone.
That is incredible. If we can perfectly model the interactions between the magma ocean and the atmosphere on Neptune, we can apply those exact same thermodynamic and chemical equations to translate the fuzzy atmospheric data we receive from sub-Neptunes thousands of light years away.
Yes. We aren't just solving a localized anomaly in our own solar system anymore. We are literally unlocking the architectural blueprint for the vast majority of planetary systems in the Milky Way.
It completely unifies our understanding of planetary evolution. It suggests this beautiful continuum. Like, instead of treating ice giants as this bizarre, isolated category of planets that only exist in the deep freeze of the outer solar system, we can integrate them into a much broader, galaxy-wide understanding of how intermediate mass planets form, how they trap heat, and how they evolve over billions of years.
It's incredibly exciting from a theoretical standpoint. It ties everything together.
It really does.
Right.
But it inevitably brings us to the hardest part of the scientific process.
Right.
We have this elegant, mathematically sound computer model from UCLA. It neatly solves the magnetic field chaos, it perfectly balances the heat transport equations, and it completely bridges the gap to exoplanetary science.
Right.
But at the end of the day, a computer model is still just a model. How do we definitively prove that there is an ocean of liquid fire churning beneath the clouds of Uranus? I mean, we can't just stare at the math forever. We have to know for sure.
No, we cannot just stare at the math. Empirical validation is the final, non-negotiable hurdle in all of planetary science. And as we noted at the beginning of our discussion, humanity has not physically visited these worlds since the Reagan administration.
Which is painful to think about.
It is. And there are currently no active, fully funded, metal-bending space missions on the manifest to return to the outer solar system right now. The tyranny of distance, combined with the sheer immense budget required for deep space exploration, means that these planets have been largely and tragically neglected.
It is endlessly frustrating to think that the literal keys to understanding the entire galaxy are sitting right there in our own solar system, and we just aren't looking at them. But I know the planetary science community hasn't given up. There have to be mission concepts on the drawing board. If a space agency decided to fund a return trip tomorrow, what would that mission actually look like?
Oh, the scientific community is actually highly organized on this exact front. Every 10 years, planetary scientists get together and produce what is called a decadal survey. It basically outlines the absolute highest priorities for future exploration for the next decade.
Right. It's their ultimate wish list.
Exactly. And in recent years, returning to the outer planets has skyrocketed straight to the top of that list. The most prominent, fully fleshed out mission concept that is currently seeking approval is known as the Uranus Orbiter and Probe, or UOP.
The UOP. And what makes this concept so vital is that it fundamentally changes the nature of the encounter, right? Because Voyager 2 was just a flyby. It had mere hours to gather data before it was hurled out into interstellar space. But the UOP is designed to stay.
The shift from a quick flyby to a sustained orbiter is monumental. The UOP concept involves a massive primary spacecraft that would utilize a technique called propulsive orbit insertion.
Meaning it fires its engines backwards to slow down?
Right. It fires its engines to decelerate enough to actually be captured by Uranus's gravity. And once it's in orbit, it would spend years conducting a sustained, highly comprehensive analysis of the planet.
So it could really map that weird magnetic field.
Exactly. It would map the chaotic magnetic field from every conceivable angle over a long period of time, specifically looking for the minute fluctuations that would definitively prove the existence of a convecting magma dynamo below. And it would utilize advanced infrared spectrometers to map the global heat flow, pinpointing exactly how that thermal energy is escaping the interior.
But the orbiter is only half of the UOP mission. The probe aspect is the part that genuinely sounds like something straight out of science fiction.
It is arguably the most daring engineering challenge currently proposed in modern planetary science. The UOP would physically detach a highly shielded atmospheric probe and send it on a direct, intentional collision course with Uranus.
I really want to break down the sheer mechanical terror of that descent, because it isn't just dropping a GoPro into the clouds. The probe has to survive plunging into an atmosphere moving at supersonic speeds, while the atmospheric pressure exponentially increases around it every single second.
The engineering constraints are extreme. The probe would hit the upper atmosphere at thousands of miles per hour, relying on a highly advanced ablative heat shield to just survive the initial friction of entry.
Which is going to generate insane heat.
Incredible heat. Once it finally decelerates enough, it would deploy a massive parachute system and begin a slow, terrifying descent deep through the hydrogen and helium cloud layers. And as it falls, onboard mass spectrometers and sensors would be furiously tasting the chemistry of the atmosphere in real time.
It's actively sniffing the air as it falls.
Yes. It would measure the exact isotopic ratios of the gases, the temperature gradients, and the pressure curves.
So it's basically searching for the chemical signatures of the boundary layer we talked about earlier. It's looking for the trace elements that the magma ocean is actively off-gassing into the upper atmosphere.
Exactly. It is looking for the empirical fingerprints of the magma. And the hardest part is, it has to relay all of that massive data telemetry back up to the orbiter using radio transmitters, fighting through the thick, increasingly dense plasma of the lower atmosphere, before the crushing pressure of the planet finally breaches the hull and destroys the probe entirely.
It is a literal suicide mission for the hardware?
It is. But it would provide the indisputable ground truth data that these computer models crave. It would tell us once and for all if UCLA is right.
And we shouldn't leave Neptune out of the conversation entirely. I know there is a parallel, albeit maybe slightly less developed, mission concept for the eighth planet as well.
Yes, there is. It's known as the Neptune Odyssey. It operates on a very similar architecture to the UOP. An advanced orbiter designed to deeply study the atmospheric dynamics, the thermal emissions, and the magnetic anomalies of Neptune. And crucially, both the UOP and Neptune Odyssey concepts place a massive emphasis on studying the moons that surround these giants.
Which might seem like a tangent to some people, but the moons are actually critical to understanding the inside of the planets themselves, right?
They are entirely interconnected. You see, planetary moons essentially act as external gravitational probes. As a spacecraft orbits Uranus or Neptune, the complex gravitational tug-of-war between the massive planet and its various moons causes minute, measurable shifts in the spacecraft's trajectory.
So you can track the wobble of the spacecraft.
Right. By tracking those tiny orbital deviations over years, scientists can reverse engineer the exact density and mass distribution inside the planet. If there is a dense, churning ocean of heavy silicate magma down there, the moon's gravitational interactions will betray its presence to the orbiter.
Plus, the moons themselves are just bizarre. Like Triton around Neptune has active cryovolcanism, literal ice volcanoes erupting in deep space. And Miranda, around Uranus, looks like it was shattered into pieces and glued back together with these sheer cliff faces that are miles high.
They are fascinating worlds in their own right, yes.
Studying how the tidal heating from the main planets physically powers the geology of those weird moons. I mean, that gives us even more data about the energy systems of the entire planetary neighborhood.
Exactly. The interconnectedness of the system is what makes sustained long-term observations so vital. We simply cannot understand the core without understanding the atmosphere, and we cannot fully understand the planet without understanding how it gravitationally manipulates its moons.
The stakes for these proposed missions just feel incredibly high. I mean, we're talking about designing intricate spacecraft that'll take a decade just to build and another decade just to travel the billions of miles across empty space to reach their destinations.
It's a generational commitment.
It really is. We are relying entirely on the precision of human engineering and the predictive power of theoretical physics. We are essentially betting billions of dollars and the literal careers of countless scientists on the mathematical probability that an ocean of fire exists inside a world of ice.
But that is the fundamental essence of deep space exploration. The mathematical anomalies tell us exactly where the mysteries are hiding. The computer models provide a map of what might be physically possible. And then eventually, human curiosity simply compels us to build the machine, launch it into the dark, and go see for ourselves if the models were right.
It is an unbelievable intellectual journey we've taken today. We started with two planets that we all thought we understood so perfectly. The cold, static blue ice giants frozen on the edges of our childhood classroom posters.
The dormant worlds.
Right. We've explored how the limitations of 1980s technology created a compelling but ultimately highly flawed illusion of total comprehension. We've broken down the bizarre magnetic chaos and the thermodynamic contradictions that simply refuse to fit the established narrative.
The anomalies that broke the model.
Exactly. And through the lens of modern astrophysics and the incredible work at UCLA, we've stripped away the ice entirely and rebuilt these worlds from the core outward. We've replaced the static deep freeze with dynamic, violently churning, unimaginably hot magma oceans, buffered by exotic chemical transition zones.
It's a much more violent, active picture.
It is. And in doing so, we've realized that unlocking the fiery secrets of Uranus and Neptune provides us with the ultimate cosmic blueprint for understanding the most abundant exoplanets in the entire galaxy.
It really is a profound shift in perspective, and I think it serves as a powerful reminder of how scientific progress actually functions in reality. Anomalous data like a magnetic field that sits 59 degrees off axis, or a heat signature that completely defies the insulatory properties of ice, that data is never something to be ignored, minimized, or forced into an outdated model.
You can't just sweep it under the rug.
Exactly. It is the exact thread that, when you finally have the technological capability and the theoretical courage to actually pull it, it unravels our entire previous understanding and leads us to a much deeper, much more complex truth. The original ice giant model wasn't a failure of science, necessarily. It was the absolutely necessary stepping stone that provided the foundation for us to eventually discover the magma.
That is the absolute perfect way to frame it. Science is just a continuous, messy process of refining our models until they finally stop breaking. And that leaves me with one final thought, something for you to chew on long after we wrap up this discussion. If we could fundamentally mischaracterize two of our closest, largest celestial neighbors for nearly 40 years, literally calling them frozen ice, when the math now strongly suggests they might actually be oceans of churning fire, what other established facts in our textbooks, foundational things we take for granted every single day, are just waiting for a new generation of scientists to come along, look at the anomalous data, and melt them away?